Okay, this is lecture 23. So we are quite close to the end of our offline lectures. So we are far behind the schedule, but we will just keep this lecture progress. And although I originally planned to discuss the state-of-the-art devices like FinFET and CFET in the recorded videos, but unfortunately I'm afraid that I cannot cover this one in this semester. So maybe in our recorded video L25 and 26, so maybe we will cover double gate MOSFETs and its related models. So please understand this lecture progress. Okay, so the previous lecture was devoted to the something related to MOSFET scaling. So maybe you remember that we have covered the roadmap by IMEC, the Belgian Research Institute, which provide us a certain roadmap for technology development. And at that time we discussed that we are around L2 node as of 2025, and we move to another advanced node from now on. So but today's lecture will be devoted to this one. These two topics will be just merged, and I will just quickly cover MOSFET scaling. So MOSFET scaling in simple way, if I have to summarize this MOSFET scaling history, then I have to say in this way. Basically, the MOSFET started as planar MOSFET. So for planar MOSFET, so as we will see from now on, so it was done around the late 90s or early 2000s. So there was the scaling of a planar MOSFET following so-called Dana's law. So I will explain later. After that, just mere geometric scattering was hit by the wall, scaling wall. After that, the engineers has introduced clever ways to further scale down their devices. There was so it is simply speaking, we can say that this is related with stress, and that was till the 2000 around 11. So at 2011 they introduced a new architecture. Architecture means that FinFET. So this was the FinFET, and we are now moving into nanosheet MOSFET. So this is maybe around 15 years we have produced FinFET, and now we are moving toward the nanosheet era. So this is the situation. So simply speaking, if I have to categorize, of course, please be careful. Nobody announced that, okay, this is the era of something. This is just a retro view. So after time has passed and we are just looking back our history, then just to categorize, okay, this is the era corresponding to certain paradigm. So please don't think that there is a clear cut and suddenly everybody just change their minds and jump into a new paradigm. However, if we can do this kind of categorize, then I would say that there is a classical or happy era, and there was also stress engineering. After that, we can say that this is the era of architectural change. Architectural change means that move to FinFET or other advanced structure, and we feel that actually by changing our architecture further, maybe we can survive with this current technology, well, around 10 more years or 15 more years. So this is a known future, so we can do with the silicon technology. Then what else? That is not that clear right now, and people are talking about how can we extend our technology further and further. Okay, so now let's go to our main topic. So today we will discuss about these two parts. The first one is Dennard scaling, and second one is stress engineering. So this is the activities in entire 2000. In the case of this scaling, so of course we are not talking about entire activities of scaling. We just think about from the viewpoint of this designer. So this guy just says that, oh, we must build our transistor in that way. However, if this fab guy can say, okay, I can build that device reliably. So otherwise, we cannot make the working technology. So although we can say we must scale down our device in that way, but if we cannot make it, then nothing happens. For example, I can say we must build, for example, just one atom thick device. Yes, we can say, but how can we actually fabricate one atom thick device? So if we cannot really make it, then this is just a meaningless discussion. So every time we have to have the balance between our design, ideal design, and also physical reality. But in this course, we are just saying that, okay, we have plenty of abilities to actually make it. So among many different capabilities, one important one is lithography. So can we make a very short channel L? So that was one thing. And also, can you make very shallow source and drain? So simply speaking, let's just say that this is the definition of our length L. This is quite short, but say that happen to be our source and drain is drawn in this way. Yes, say that this is a source and drain. Then what will happen? In this case, it is sure that, okay, near this part is completely controlled by our gate. However, there will be direct communication of charges between source and drain. So therefore, if our source and drain regions are too deep, then this is far from our gate terminal, not controlled by gate. So it means that there occurs a certain unexpected current conduction. So simply speaking, if we reduce the length to get performance advantage and area advantage, then of course we should scale down our depth, vertical depth also. In this case, actually the ion implantation played a critical role to control this depth. So make it shallow. For example, I wanted to make it just a shallow junction and shallow junction. Say in this way, it is quite easy to say. I wanted to make it just a 10 nano thick junction, 20 nanometer thick junction. It is easy to say. Please make it. However, how can we actually make it? With traditional way, diffusion, so it was very difficult to control this depth, and number of atoms in it, it was also very difficult. However, by adopting ion implantation and precisely controlling the ion implantation energy, so we can control the number of incident atoms and depth profile of this incident atoms. So that was two important technique to make our device working. Of course, there are tons of other ones like etching and also kind of a CMP, and also not shown here. However, how can we improve the interconnection? There are many other ones, but roughly speaking, we will assume that okay, anyhow, this can be done by our very powerful fabrication capability. We believe it. Our role is just to design the best device given design rule. So that will be our role. Okay, so are you with me? So now let's go to this slide. So this is a constant field scaling, or that is called as Dennard scaling, following very famous engineer Dennard, who invented DRAM and also proposed this scaling law. So you know what is DRAM? DRAM is the DRAM you know. So that is a memory device which have a single transistor and single capacitor, and by storing certain charges in this capacitor or not, so we can just write down information 0 or 1. So 1 bit is stored by this one transistor and one capacitor. This is maybe this is the smallest memory cell we can imagine. Of course, I have to be a little bit careful. So of course, in the case of NAND, maybe you have, all of you guys have a USB disk at your pocket or your dormitory room, so use it for your personal purpose. But in that case, actually, one single device can memorize 2, 3, or even 4, 5 bits in a single device. So if we consider just density of information stored a given volume, then maybe in the case of a NAND memory, we have a higher density. However, this information is a little bit difficult to access. So in order to access certain information stored in that NAND, we have to wait a little bit longer. However, in the case of this DRAM, it is very easy and quite quick to access this information, stored information queue. So that's the reason why in your system, called as so cell phone, PC, everywhere, we are using DRAM as the main memory. So think about this system. NAND is also a memory. DRAM is also a memory. However, when you say that memory, so CPU's or your personal computer's memory, what is the capacity you are working on? So in that case, when you have a NAND, so usually nowadays it is called as SSD, solid state drive, then this is just regarded as storage, not memory. But when you consider your CPU or your PC, then you say what is the size of our DRAM. So simply speaking, DRAM is regarded as a memory device, and SSD or SSD made of NAND, and that is regarded as storage instead of the main memory. Okay, so anyway, Dennard really invented this DRAM, so he is the real pioneer in this field. But he also contributed this scaling rule. So following his name, this one is called as Dennard scaling. The main philosophy is quite simple. We wanted to keep the field inside our device the same. It means that when we have a certain node n something, and if we move to n, the next node plus 1, usually what we wanted to do is to scale down our devices. So why don't you just come to okay, so I'm afraid that I don't have it. So let's have a look at this one. Say that this is the present node and this is the next generation node. So they are, for example, let's say they are scaled. In this case, we have smaller device compared with the given device size. So simply speaking, let's just say that we have introduced, for example, say scaling factor kappa. So here we introduce a scaling number corresponding to kappa, and which is larger than 1. Sometimes people wanted to introduce a certain factor smaller than 1, but they are the same. Let me just explain. For example, in our terminology, usually our kappa value, traditional value for kappa was 1.4. So it means that we wanted to, how can I say, we wanted to decrease our dimension of 1 over kappa. This is corresponding to 0.7. So maybe you can understand the product between 1.4 and 0.7 is quite close to number 1. So please remember that these two numbers. So anyway, the typical way is when we have a present device, then this is almost given that in the next device we wanted to build 0.7 times smaller device. For example, let's say this is 1 micrometer technology node, and then we wanted to make for example 0.7. Although there is no such a kind of thing in reality, but anyway, say that there is a certain rule. The point is, okay, when we consider the minimum length, so previously the minimum length was L, and now our new minimum length is L over kappa. Please note that since kappa is 1.4 around something, so actually this is corresponding to 0.7 L. Length is reduced. Then now let's say we keep this device maximum voltage just as before. Still this is VDD. Then please try to find out the average electric field inside this system. If everything is just uniform, then what we can say is previously the length was L and the voltage difference between source and drain was VDD. So electric field was given as VDD divided by length L. That was the previous case. And now if we just keep this VDD value and reduce only length, then we have to have this one. Simply speaking, we will have kappa times higher electric field inside our device. So are you with me? Previously, let's say that L value is 10 micrometer, and say that VDD equal to 5 volt. Then previously we had 5 volt divided by 10 micrometer. However, if we introduce 7 micrometer technology, for example, then in this case our electric field will not be this number, but increased by factor of 1.4. Yes, electric field is increasing. But does it matter? Yes, actually that really makes a big problem. So another scaling simply says that instead of allowing increase of electric field inside this device, just to keep this electric field. So by scaling all other geometric parameters. So simply speaking, it is combination of geometric scaling and voltage scaling. Simply speaking, here please have a look at this one. When you have a look at this present technology and the next technology, every length scale is scaled by just 1 over kappa. So this is L, and length is scaled, and also this vertical scale is also quite much scaled. For example, previously it was T oxide thickness, and now you can see that this is T ox divided by kappa. In this case 1.4, so we will have a thinner oxide thickness. Everything is just miniaturized without much certain distortion. So simply speaking, if we have a certain Lego figure, then just to make it smaller, yes, this is the way to make this new technology. Then if we do not scale down our voltage, then since the length scale is scaled, electric field will be increased. However, by scaling voltage altogether, we can keep the constant electric field inside this system. This is another scaling law, and that works quite well. So please have a look at. Let's just make a simple discussion. And as I told you before, certain depending on literature, sometimes they wanted to introduce kappa or other symbol in a different way. For example, when you find certain kappa equal to 0.7, then please regard it as just the inverse of kappa. So that's pity, but there are certain paper which use the scaling factor lower than 1.0, or sometimes they have the scaling factor higher than 1.0. So now, simply speaking, all of device dimensions are scaled, and doping concentration is increased, and also voltage is linearly scaled. So that was the rule. Then by doing this job, we can find some things. So maximum drain depletion width is scaled. So just to put scaled version of your voltages here, voltages and doping. Doping is increased and voltage is decreased. Then by taking this number, you can find that depletion width is also scaled. So it means that we are now achieving this goal. Previously, here we had certain depletion width in the drain side, and that is also scaled down in this miniaturized device. However, please be careful. In order to make this kind of operation, so we have certain unscaled factor here. We have built-in potential. So although we have reduced the voltage quite a lot, however, here we have a built-in field, and we believe that more or less in the initial stage of our technology development, this second term was much more dominant than this first term. So please think about this one. What is built-in potential. Built-in potential means that the built-in potential between n plus region and p-type substrate, and its value was about just 1 volt. And previously VDD, we started from 5 volt VDD case. So this was 5 volt and this is just 1 volt. So multiplying 0.7 to this one. So let me just give you concrete number. Previous value was 1.5. However, now it is moved to 0.7 times 5. So it becomes just 4.6 and 6. So simply speaking, this is corresponding, although this one is not scaled, but at the initial stage of our technology scaling, it works because it was relatively small portion of our potential difference between drain and substrate. But after time has elapsed, so we have reduced our voltage again and again. After that, finally we have reached the values like 0.7, and still this value is about 1.0 or something. So it clearly means that now, although we can try to scale down our operation voltage, but that does not scale down our depletion with any further. So simply speaking, this Denner law looks quite okay. However, there is certain range for its validity. So anyway, so in former technologies, it was completely okay. And also, how about other parameters like capacitance? So capacitance is given as capacitance of a given system is given by epsilon and divided by T ox and W and L. We need this one. However, capacitance in this case, width is reduced by kappa, 1 over kappa factor, and also length is scaled by 1 over kappa factor, and also this T ox is divided by kappa factor. So we have this kind of scaling rule. So please have a look at them. So finally, if we go to drain current, so then this is the original expression for our drain current, and now it is scaled by this 1 over kappa. Please note that kappa is given as 1.4. It means that the drain current is actually reduced. Oh, do you like it or not? So please think about this. So previously you had a certain device, and now your device is scaled down in this way. Previously 1, and now it becomes 0.7 and 0.7. So area is scaled by factor of 0.5. But now current is scaled down 0.7. Previously you had ID, and now you have 0.ID. Oh, our device now become weaker than previous case. Actually, it's not, because this is a length scale and this is a width scale. So width is scaled by 1 over kappa. So if we normalize it by its width scale, then the drain current normalized by its width is kept as before. So this is quite a good property. So simply speaking, we can think about the delay of our system. Then yes, circuit speed please think about the main motivation of this scaling. Why we wanted to try to do this kind of scaling, starting from this one by one technology. If we introduce this 0.7 by 0.7 technology, the area per unit device is just to become a half of it. So for given area, when area is fixed, we can integrate twice more devices into it. That was the main motivation. We can make it cheaper. So it means that even without improving our performance, we can make twice more chips. So that was the initial motivation of this scaling. But the effect of scaling was far beyond that. When we make it miniaturized, yes, we get twice more devices, and at the same time also, yes, delay is quite much scaled down. So when you have a look at those numbers, here we have 1 over kappa square, kappa, they are actually cancelled out, and you can see that kappa tau, this is corresponding to the delay of our logic gate, is scaled by 1 over kappa square. So simply means that when, or even though we initially scale down to get economical advantage, however, the resultant word is at the same time we can get also even higher performance. That was achieved in this semiconductor industry. This is quite peculiar. Oh, think about this one. Think about your car industry. If you have a very luxury car, so in order to sell more cars, of course you can reduce the size of your cars and make it smaller. Yes, that is quite an economical approach. But do you expect that when you build a smaller car, yes, this is cheaper and maybe more market competitive in the current contemporary market, but do you expect that that outperform your previous one? So you have a big car and smaller one, but that outperform much faster, and that is quite an unusual thing. However, in this case, since our main operation is related with movement of our electrons or holes, and scaling, the length scaling is directly reduce the final distance between starting point and end point of its journey. That's the reason why we can eventually get also performance boost in addition to the area efficiency. So that was the situation we have enjoyed quite a lot, and now we wanted to move to the second phase of scaling. So I just dig out our conference papers, previous conference papers, and I just took represented papers for each node, and you can find the name of two companies, Intel and TSMC. And what is this arrow says? In this 16 nanometer node or 14 nanometer node, you can find two companies are shown together, and except for this line, so you can see that what is the company name and what is the company name. So actually it means that the dominance or technology leadership is very difficult to get, and once it is secured, then it takes quite a lot. I mean that quite a long time to liberate it. So that is a very serious thing we have to consider. as an engineers in in Korea. So here you can see that, of course, this is the first paper shown here starts from 2000. However, what was the history? Yes, there were several devices or technologies following the Dennard rules. Even at that time, people overcome many difficulties. But if we see from the viewpoint of current difficulties, so maybe we can see that, okay, at the initial stage, technology challenge was not as severe as ours. However, at the time, they had limited tools and limited capabilities. They really did their best to improve or cope the challenges. But anyway, so please think that, okay, up to here, although they had their own challenges anyway, more or less Dennard scalar law works well. And now something happens in this 130 nanometer node. So please remember that what was then the previous node. Well, if 130 nanometer is this current node, then my question is, what would be the previous node? If you wanted to get the previous node, just to multiply 1.4, because from the viewpoint of a previous node, by multiplying 0.7, they will get this 130. Then what will be the value? The value will be 180 nanometer. So 180 nanometer was quite successful worldwide. Even nowadays, as of 2025, you can find several surviving 180 nanometer node commercially available, because that was so much successful. After that, at the time, there are so many, compared with the situation in today, there are so many companies fabricating the devices. But of course, even in that case, Intel was the first, and they announced the most advanced node, because at that time the most significant application was, of course, CPU, and CPU market was dominated by Intel, so they needed the state-of-the-art device. They wanted to provide the best performance, so that's the reason why they have their own fab, and their fab generate the state-of-the-art devices. So anyway, now let's go to the first symptom of a certain problem. 130. So this was 130. Yes. So 130 nanometer MOSFET, and at this time the major improvement was copper interconnection. So this is a really big deal. Even nowadays we are using copper. Copper is very good metal. So although copper is almost a perfect metal, however, people could not use copper in the manufacturing, in the chip manufacturing, because copper was so good to penetrate into chips, and when copper is found in silicon, it is used as a strong defect. Once copper is found in silicon, then the chip is gone. So that was the problem. So Intel guys, or not exactly Intel guys, I'm not quite sure. So engineers have introduced a certain technique to make a certain layer which prevent the diffusion of copper. So once make this barrier layer, so this is quite much good for confine kappa. So when kappa is here, without this barrier layer, it can propagate, diffuse. However, this barrier layer just to prevent diffusion of kappa that was developed in that time. So it is already 25 years ago. After that, we have enjoyed kappa interconnect quite a lot. Even nowadays, kappa is regarded as the best one. But point is, since nowadays interconnects are scaled too much, so now we feel that it is a little bit too expensive to keep this barrier layer. So think about this one. If we allowed a certain cross section, okay, this cross section is allowed for metal interconnect. Then in our current situation, we have to introduce certain amount of thickness for our barrier layer, and only for certain part, yes, we can fill kappa. So although we are allowed to use a certain cross section, the barrier metal, which is just to keep kappa inside it, that reduce. Of course, this one is not that good metal, as good as kappa. So that reduce the overall performance of this kappa interconnections. Previously, when our scaling rule were quite large, then small one very narrow or shallow, this barrier layer was not that problem. However, now we have shrunken our device quite a lot, so therefore this barrier layer is no longer negligible. So that is one thing. So maybe you have, if you are interested with this technology, maybe you have heard about other materials currently used for this as an alternative to this interconnect, but it has also its own problems. So I don't know what will happen. So simply speaking, kappa is extremely cheap, so really good. So and there are a lot of kappa on the earth, so it is easy to find it. But alternative metals are rare metals. Actually, they are expensive, and we have to have some special care for their supply. Well, anyway, think about this one. At 130 nanometer technology, operation voltage was 1.3 volt, and oxide thickness, this is important, oxide thickness is 1.5 nanometer. Why it is important? So yes, please have a look at this one. If we have 130, then please multiply 0.7. Then what will be your answer? Your answer will be 91. So that's the reason why we call it as 90 nanometer technology. So then please, if we just follow the oxide thickness also scaling rule, starting from 1.5 nanometer, please multiply 0.7. Then what will be your answer? If you just follow this multiplication, then you will find that this is corresponding to 1.05 nanometer for your next node called as 19 nanometer node. But actually, the one we have at 19 nanometer generation was this is really 1.22. Maybe you can ask me this question. Well, 1.22, 1.05 seems to be just 0.15 nanometer difference. This is just 1.5 angstrom difference. So is it really detectable, or is it really important? Yes, that is critically important. So the reason why they failed to build just 1.05 nanometer thick silicon dioxide layer was, now since gate oxide becomes too thin, if we reduce it just to 1 nanometer, then what happens is, now here we have a silicon and here we have a gate, and we collect many electrons by introducing high gate bias voltage. So now think about this one. Here we have gate voltage equal to, in this case, well, I'm not quite sure what is the value over this technology. So let's say that just 1 volt, let's say gate voltage is 1 volt, and this is 1 nanometer oxide thickness. Then what will be the electric field? Its value is corresponding to 1 volt per 1 nanometer. 1 nanometer is, in terms of centimeter, it is 10 to the minus 7 centimeter. So simply speaking, by calculating this number, you can find that the number is corresponding to 10 to the 7 volt per centimeter. Simply speaking, just 10 megavolt per centimeter. So this is quite high electric field even for this silicon dioxide, and for this high electric field, now our electrons feel strong yes, acceleration or attractive force toward gate. And previously the oxide thickness was not 1.0 nanometer, it was 1.5234. Then there is no possibility to overcome this physical barrier. However, since now it becomes too thin, it can just directly overcome this very thin oxide layer, 1 nanometer thick, and arrive at gate. So simply speaking, now we have gate current. Gate current originated from electronic movement from channel to gate directly by tunneling. So it happens in this extremely scaled gate oxide. That was the problem. So in this 90 nanometer node, oxide thickness was not decreased or scaled by the nominal factor like 0.7. They failed. Of course they tried, and they found that, oh, oxide gate current is too high, so we cannot live with this technology. So that's the reason why, okay, we just compromise at slightly modified value, compromised value. So then what will be the result of this compromise? Since Cox is given as epsilon oxide divided by Tox, oxide thickness, if we reduced it by factor of 0.7, we will get increase of expected oxide capacitance. But now it is less, so what we have obtained from this one is Cox is not scaled as expected. It means that we cannot get sufficient amount of electrons expected for new technology. Previously, every time when we scale down, we successfully scale down also particle structure, and for given width or given area, we were able to get more and more electrons, and it was always exponential or having the constant ratio. However, that growth rate is now slowed down. So then everybody in the market are expecting we can get once again improved device, but our intrinsic channel is not as powerful as the expectation. So what can we do? So they have introduced different way to improve the performance. It means that they have introduced silicon germanium for PMOSFET and also silicon nitride capping layer for MOSFET to improve what? Improve their mobility. So they wanted to have a certain level of current. However, COX is not improved. So you know that current is given as a function of some quantities, and you can see that we need COX improved. However, if it does not meet the expectation, so what we have done is, okay, just stay there, and we can instead increase this mobility. So mu and COX product is entirely increased, so they met the expected values. That was the one we have in 90 nanometer node. So as you can see, in order to get this performance boost, in the case of a PMOSFET, we need silicon germanium. And also in the case of a MOSFET, we need a silicon nitride. It means that depending on the polarity, we have to introduce different stressors, the technique to apply stress into our channel. So it makes our device fabrication process even more difficult. So when we consider this N-type, then we have to mask our P-type device and introduce a certain stressor. After that, also the other way around, we have to do it. And of course, they should not affect the others. For example, in order to get improved electron mobility, we do something. Then it should not degrade the whole mobility of a PMOSFET. So they are cross-correlated, and engineers should be very careful not make any harm for the other devices. So now it becomes even more difficult. So anyway, now you can see that this is just a typical TEM image. So here you can see silicon germanium and silicon germanium. And silicon germanium compared with just normal silicon germanium has a higher volume. So when integrated, then this guy, so think about this one. Here we have an airplane, and in our airplane there are 3 seats, and there is one normal guy and there are 2 big guys, and they should sit in a row, and big guys are there, they are big, and this guy is just normal. Then what happens? The central one feels certain stress sent from these 2 surrounding big guys. That happens to our silicon channel, and when that happens, when our silicon channel is compressively stressed, then it is known that its whole mobility is increased. So that is the main reason why we get improved whole performance. This is quite important, really important, because even nowadays our technology, new technology, there can be many different options, but we follow certain specific technology, because in order to improve hole mobility, we need silicon germanium source drain. So that's the reason why we have to have certain technological option. Okay, so maybe okay, this is the time to say about this one. In my original plan, I have a separate lecture for CFET. However, I'm afraid that we have no further time, so I have to say it now. So nowadays we have a technology option called as CFET, complemented field effect transistor. Please don't be confused with CMOSFET. CMOSFET is the MOSFET we are now currently talking about. Then what is CFET? This is also a kind of a CFET. And what is C? This is complementary. What is C? This is the same complementary. I'm not kidding. But this is the common use of this terminology. So they say that instead of making our device MOSFET and PMOSFET all together from the top view, they just build one device which have NMOSFET at the same time PMOSFET. So simply speaking, MOSFET is just placed over PMOSFET. That is called as CFET. In this case, maybe we can have two different options. One option is place our PFET in the bottom and place our NFET on top. This is one option. And the other way around is place our NFET bottom and also place PMOSFET on top of N. This is two different options. However, our current technology always prefer to have this bottom PMOSFET option. This one is never considered. Why? Because using this technology, this option, now we can introduce silicon germanium and silicon germanium, so our PMOSFET mobility can be just kept as before. However, if we place our PMOSFET on top of MMOSFET, then our silicon germanium stressor is not as effective as the one shown here. So that's the reason why we have bottom PMOSFET and top MMOSFET option for our CFET. So this is really critical. So improving hole mobility by using silicon germanium source drain, this is still very important, critically important technology option. Please note that 90 nanometer node was announced in IDM 2003. This is 22 years ago. However, still we are enjoying this technology quite a lot. And yes, there is a MOSFET. In the case of MOSFET, if we follow this silicon germanium, then it is known that hole mobility is improved. However, at the same time, electron mobility decreased. So in this PMOSFET, electron mobility is degraded. But it's okay because we do not use electrons in our PMOSFET. However, in the case of MMOSFET, we are using really electrons. So in this case, it is known that we need to have tensile stressed silicon channel. So what we do is here, this is a silicon nitride channel. So silicon nitride channel is placed, so it has more volume, so it just difficult to say, but by introducing this stressor reason, so we can just introduce tensile stress to our silicon channel. So by introducing stress engineering, so you can see that these two graphs. So this is if I'm oh yes, this is the electromobility and this is whole mobility. And please have a look at this solid line. This solid line is corresponding to universal curve. Do you remember universal curve? So as I told you before, if we measure electromobility or whole mobility as a function of so-called effective field, although fabs are different, but all of them show one single curve. So that is universal, and people thought that we never beat this universal curve in a MOSFET. But by introducing this tensile stress, so we can increase electromobility about 6%. And in the case of a hole, by introducing this compressive stress, we were able to increase our whole mobility about 10%. Well, to you, maybe 10%? Is it important? Critically important. In terms of chip manufacturing, just 1% difference is regarded as meaningful and significant changes. So they really careful about this. 10% is just like just something big. So now they have introduced the stress quite a lot. And yes, that was the situation in 90 nanometer case. Then please just to try to keep this play. 90, now you have 90, just to multiply 0.7. Then what will be the number? 63. So we have 65. And once again, please multiply 0.7. Then you have 45.5 maybe. Then you have 45. 45, when you multiply 31.5, yes, you have 32. You can understand this some nanometer always follow the rule like multiplying 0.7 something. So yes, you know this one. After that, this is 22, and multiplying this 0.7 once again, you have 14 or 16, because the number will be 15.4. So some says that 16, some says that 14. After that, if we follow just 14 nanometer scale, then that will be 10, 7, 5. They are really following the naming convention. 7 multiply 0.7 will give you 4.9. So this is 5. And now what is this one? We have a 3.5, but we say 3. And once again 2.1, but we say 2. That is the naming convention. Then the naming convention was actually the meaning of this naming was lost somewhere here. Yes, around the FinFET era, we lost its physical meaning. So this is no longer possible. So more exactly, Intel try to keep this meaning of this 14 nanometer down to 14 nanometer, because I guess that since they are the guys to enjoy this scaling rule most, so they wanted to keep this rule as much as possible. There are other companies, Samsung, TSMC, other guys, they were just following Intel, and they less careful for following the legacy, because the legacy is not theirs. The legacy was Intel's. So they introduced certain new technology having different, having certain number, but does not follow the scaling rule. Now the name is just routinely generated by multiplying 0.7. So now it becomes a marketing one. So maybe you now heard about Intel's 18A node. So nowadays there is some buzzwords about this technology. Intel is nowadays talking about, oh, we will make a 18 Armstrong node and soon it will be delivered to the customers. So 18 nanometer means that this is 18 Armstrong, so it is corresponding to 1.8 nanometer. However, there is no real 1.8 nanometer in that technology. That is regarded as just naming convention. Every company nowadays using these numbers as just to design or designate their new technology. Introduce a small number and just name them. Okay. So anyway, now let's go to 65 nanometer node. And 65 nanometer node also we have a really big change here. This is high K metal gate. High K means that K is nothing but just permittivity, relative permittivity. Sometimes we use epsilon to show permittivity. However, sometimes we use also kappa to say permittivity. They are interchangeably used. So high K means that kappa. So simply speaking, we now introduce very high permittivity material. How high is it? Its value is known to be about 20.0. Ideal value is 22, but in reality about 20. Is it really true? So silicon case, its value is just 3.9. We have told this number again and again. And if we adopt a high K material, its value can be increased quite a lot, like 20. It means that more than 5 times increase in its permittivity. It means that 5 nanometer thick high K material in electrical sense, as in terms of its capacitance, it is corresponding to just 1 nanometer thick silicon dioxide. Although that is quite thick, but in terms of its capacitance, it is just like 1 nanometer one. So that is really big deal. We wanted to reduce oxide thickness, but the oxide thickness we wanted to reduce is not its physical one, but it's electrical one. Actually, what we wanted to do is Cox is given as epsilon over T, oxide thickness, oxide permittivity. We wanted to increase it. In order to increase it, we wanted to decrease this Tox. That was a previous case. However, in the case of high K material, instead of reducing this one, now we increase this oxide permittivity of oxide. Then now we have sufficient room to have thick oxide. So why it is important? So the reason why we failed to scale down our Cox was so gate leakage current. Gate leakage current was so severe, so we had to introduce some unscaled, less scaled Cox value, but now we can once again scale down our effective oxide thickness. So now maybe if you are working on this field, maybe you will say oxide thickness. However, this oxide thickness sometimes should be regarded as not physical one, but electrical effective thickness. Although your layer is high K, but please consider it as a silicon dioxide and calculate the corresponding thickness. Simply speaking, although in this example, although your physical thickness is 5 nanometer, but please regard it as a silicon dioxide layer, then you will find just 1 nanometer as effective thickness. That is the one we will have now. So please think about this one. Let's say, let me give you some very simple idea. We have a 0.7 nanometer thick silicon dioxide layer, and say now we have a 5 nanometer thick high K metal layer, and happen to be its permittivity is given as just 5 times of oxide thickness, so say that 19.5. In this case, what is the effective T-ox of this layer? Effective thickness of this this high K metal stack or high K oxide layer is simply given as 1.7 nanometer. So are you with me? Why it is 1.7? Because this 5 nanometer high K layer can be regarded as just 1 nanometer oxide layer, and here we have the real oxide layer whose thickness is just 0.7. So the overall thickness will be just 1.7 nanometer layer. Why I'm talking about this silicon dioxide layer? Because actually the attachment between silicon and high K material is quite poor, so we cannot attach them directly. So the trick is to introduce very thin silicon dioxide layer once, and on top of it we build this high K metal layer. So our current oxide layer should be regarded as just a multi-layer. Inside it, it has a certain oxide layer and high K layer, something like that. And actually, the exact recipe is not known to us, because this is also secret, the industrial secret. But anyway, this will be the one. The problem is the required value for our effective TOX nowadays is about less than 1 nanometer. We really need, for example, 0.7 nanometer or 0.6 nanometer for our next generation technology. It means that actually even with this one layer of a silicon dioxide layer that is consumed by this specification. So there is no room for us to introduce additional high K layer to prevent gate current. So that is also quite a big trouble for our industry. So because we wanted to ever increasing COX value, however, we are already quite close to the end of this scaling. But anyway, at the time, it was really amazing and solved many problems. Suddenly, the physical thickness of our oxide layer becomes more than several nanometer, so it's completely suppress the gate current. So there was no gate current problem at all for a long time. So yes, so I think that this is the final slide in today's lecture. Starting from 130 nanometer, they have introduced many innovations. So it means that not just following another law, but now you understand they have to introduce some physical effect to further improve the performance. For example, strain silicon, stress, and high K. By adopting this one, if we consider drive current normalized by width, and it is increased quite a lot. So starting from certain number, now we have much higher number. So my final word is yes. Please have a look at this number. This number scale, unit scale, you should remember milliampere per micrometer, or sometimes microampere per nanometer. They are the same. So 10 times the scale, and in this case, state of the art device should have some numbers like 1, 2, 3. So please check your own device, whether your own device has how large number for this one. So there are not many technologies which can achieve this number. Of course, if you consider very exotic technology, for example, certain compound semiconductors, you can have a quite high value, like number 9, even 10. That can be allowed it for your special technology. But in the case of a silicon technology, this number is around 1, 2, something like that. This number should be remembered. Okay, I have not covered all over this scaling part, but in this Wednesday, also I will start from this FinFET and quickly cover FinFET and move to this next part, quantum effect. Thank you.